Hello, everyone. We appreciate you taking time to join us today. Microbial Insights is delighted to have Dr. Julio Zimbrón, the founder and president of eFlux, and also Dr. Sam Rosolina, R&D director at Microbial Insights. Julio and Sam will be discussing about the natural source zone depletion processes and addressing the risk of contaminated sites in a cost-effective manner. Dr. Julio Zimbrón is the founder and president of eFlux, a company specialized on environmental measurements related to groundwater NAPL contamination sources. He received his PhD degree in chemical engineering from Colorado State University in 2000. Dr. Zimberon's experience includes environmental consulting, industrial research and development, and academic research. His work in areas of natural source zone depletion and NAPL distribution and mitigation includes 6 patents, numerous technical papers, and contributions to guidance documents. Dr. Zimberon presents multiple times a year at national and international conferences and workshops. Also, we are happy to have Dr. Sam Rosolina as our next speaker. As Director of Research and Development, Sam works with each of the laboratories within Microbial Insights and collaborates with experts across multiple industries to continually drive innovation forward. Throughout the development of new molecular biological tools, his focus is a balance of hard science, accessible methods, and actionable data. He received his BA in chemistry from Berea College and went on to complete a PhD in analytical chemistry at the University of Tennessee. Throughout his PhD research, Sam focused on analysis of trace-level trace-level environmental toxins, including heavy metals and toxic gases, detection and quantification of trace contaminants in a complex mixture and media is an especially challenging field, requiring not only the development and optimization of innovative new analytical methods, but also the establishment of highly rigorous QA/QC procedures for initial and continuing method validation. So please note that this webinar is being recorded and will be available in the resource section of Microbial Insights website within the next week. A link will also be emailed to everyone who registered for the webinar, so no need to contact us. After the presentation, we will have a short question and answer session. Feel free to type your questions throughout the presentation, and our speakers will answer as many as possible at the end. Without further ado, I will turn it over to our first speaker.
Thank you, Ali, for inviting me. Thank you, Sam, and thank you to Microbial Insights. I appreciate being here. So as Ali indicated, I'll be talking about natural source and depletion, and I want to start this webinar with short video that we made for LinkedIn posting with posing a question related to these processes in the ground and what can they do, how they matter. So the question is if the mass losses of contaminants can affect the management of these sites. And this picture shows a contaminated source, a core. It showed in which some bubbles are shown surrounding the contaminant, and the question is, can NSZD affect the estimation of remaining contaminant mass? And just kind of to give it away is yes, but there's a lot more to that. There's many other things that you can do with NSZD, and NSZD should be a very useful tool to build your conceptual site model. So this is the outline. I will be talking about microbiogeochemistry of NSZD, some things that you can do to understand if NSZD is happening, NSZD characterization, and how you measure the rate at which it's happening at sites, building the conceptual site model. I'll be presenting some reported field rates and how they compare to active remedies. I'll dig into some hard data for a case study, and I'll wrap up with some of the things that are happening in the NSZD world currently before providing a summary of this presentation. So the background is that when you have a petroleum spill, it typically happens close to the surface, and then it sinks through the vadose zone. And this spill really encounters different layers of different transmissivity. So there's some lateral movement, but it's mostly vertical. And that happens until it finds the water table. The water table, because of the buoyancy of the NAPL, the vertical movement is not as strong, and then there's some lateral distribution. Of course, this lateral distribution is very strongly affected by changes in groundwater. But here, the main concern is that part of the NAPL dissolves and affects the groundwater quality. And this is a similar picture to the one that I posted on the video. That is a core from a contaminated source. This came from about 12 feet in depth. And what it shows is that the soils are stained black because the sulfate precipitates as metal sulfides. And you also have these bubbles of biogas here. And you can see this consistently at any site. If you put this core in a sandwich bag, you'll see that there's a very strong concentration of methane and CO2. Now, typically, people were focused on groundwater quality, and in groundwater, what you see is the halo of the dissolved contaminant around the source, but you also see some important changes in the geochemistry. So you have these different reactions happening depending on what electron acceptor is used to degrade the contaminant. So you have these halos of different geochemistries in which electron acceptors are used sequentially according to the energy that they provide to microbes. So really, microbes follow thermodynamics. And this picture here on the right shows the sequence of these electron acceptors in which they are used based on how much energy they generate for microbes. And you start with oxygen. If it's available, it's the one that is used up. Then nitrate, metal oxides, sulfate, and then ultimately methanogenesis. So you see these halos in the groundwater because the groundwater is loaded with these electron acceptors. But in the vadose zone, things happen differently. In the vadose zone, you don't have typically these influxes of electron acceptors, and really you're operating at both ends of the electron acceptor ladder. So at shallow depths, you don't have methanogenesis is occurring, and that produces methane and CO2. And both of these are highly mobile in the ground, and they move upwards. When the methane moves close to the shallow surface and encounters oxygen, which is known as the anaerobic-aerobic interface, then it breaks down into CO2. So really in the vadose zone, you really have only two processes: methane close to the surface and methane oxidation. Methane oxidation close to the surface and methanogenesis close to the source. This is from the ITRC guidance document. It is a plot I put together for contributing to that document. So here is a slide from some data from a paper that Maria Reno from CSU published in 2016. I am one of the co-authors, and what she did is she went to a petroleum contaminated site, and she got some soil cores, and she extracted the cores for total contaminant. This is the scale of the contaminant, and here this is the contaminant concentration with the soil column, and then she extracted the genetic material. And what she found is she quantified archaea and eubacteria, two different types of microorganisms. And what you can see here is the highest concentration of contaminants, about 4 meters, but the highest concentration of microbes is really the aerobic-anaerobic interface. She also quantified the concentrations of oxygen, methane, and CO2 in the gas phase. And what you see here is that close to the contaminant source, there's and the groundwater surface, you have elevated methane production, but it gets consumed when there's oxygen. So Maria extracted the DNA, quantified the genetic material, but also quantified the composition of the microbial population. And that is what is shown here. And there's a lot of information here. I'm not going to go into detail here, but I just want to point out that really at this spike, what she found is a high concentration of what probably is methane oxidizers. So at every level, you have a different bacterial population, and it's adapted to doing different things. These bacterial populations are complex, but are consistent with the rest of the conceptual site model. And as I said, this is from 2016, so a few years ago, and I'm sure that Microbial Insights will have a lot more information about some ideas that you can get to collect this type of information. So how I described, some of the things that happen and consistent with natural source and depletion, but now really the main purpose is how do you quantify these rates? And you do that based on an engineering technique called defining a control volume, which is defining this imaginary envelope around your source, and then quantifying how fast things are going in and out of that envelope through the control surface. And you have fluxes that are moving across that surface of dissolved species that are associated with groundwater, or fluxes that are associated with the gases that are moving vertically. Paul Johnson and Paul Lundergaard in 2006 published a paper in which they compared the mass losses associated with the fluxes in groundwater to those in the gas phase. And what they found is that the gas phase losses were up to 2 orders of magnitude larger than those that you could quantify in the dissolved phase. And the reason is because methanogenesis produces gases. These gases are more likely to show up in the gas phase than in the groundwater. So since then, the focus has been shifted from groundwater, which was originally, to the vadose zone. So this is really a summary of some of the things that you can do. You can look at the groundwater and gas geochemistry. You can extract soil cores and do a lot of analysis there. I didn't mention this, but microbes are highly selective. They degrade contaminants that are more biodegradable initially and leave the less biodegradable behind. So the hydrocarbon composition as it weathers changes. And then you can look at these methods to quantify how fast these processes are happening. And the method that Paul Lundergaard and Paul Johnson used in their 2006 paper was to take discrete gas composition samples at different elevations and fit that to a diffusion model called fixed law diffusion. And that is called the soil gradient. But about 10 years ago, Uli Meyer at the University of British Columbia and his group, they borrowed an agronomic technique. So they realized that they could draw the envelope at the surface for the control volume and quantify the fluxes at the surface using these dynamic closed chambers. So it's a closed system that you put on the top and see how the concentrations inside the chamber are changing of CO2 and quantify the rate of gas flux that way. What I saw at the time, I was working at CSU, and I saw that was a really cool idea, monitoring these fluxes at the surface, and collaborating with Dr. Sell at the Center for Contaminant Hydrology. He posed this question: can we quantify these rates with a sorbent? And really, with very little information, we started working on this and developed this idea that you could capture the CO2 as it leaves the ground with a passive trap. And that's the trap method. There's some other methods. There's the reaction in which methane burns into CO2 is exothermic, so it produces a thermal footprint. So you can do a heat balance around this reaction and try to determine the degradation rate. I will leave that at the end because people have been working on it for a while, and the data is not always consistent, and I'll provide some references to that regard. There's one that is not shown here in the slide, which is the compositional change method, and I will cover that towards the end as one of the current developments. So how can you use these natural source and depletion rate measurements? These are the different techniques. These are the traps that I helped develop at CSU. And the idea is that you put a receiver pipe at the surface and then couple a trap. The trap has this porous sorbent, and when the CO2 leaves the ground, it gets trapped into the sorbent. But there's ambient CO2, and you want to keep that away from your measurement. So really our traps have these two layers. The upper layer keeps the ambient CO2 away from the measurement. And I am showing two colors here because really the soil CO2 can have two origins. One is molten carbon that all soils produce, even those that are not contaminated, but really the one of interest is the oil carbon, which is the fossil fuel CO2. Locally, there's radiocarbon techniques that we routinely use for that. And this is how the implementation looks like. You have this shallow receiver, only about 2 inches in the ground. You put a coupler, a rubber hose coupler, and put your trap on top of it. And we put a little rain cover, but really there's unimpeded gas flow from the ambient into the soil and backwards. The field efforts are minimal. There's no power nor moving parts. This technique quantifies the time-integrated flux, which is the long-term flux over multiple days, typically 2 weeks. It quantifies processes due to gas flow due to diffusion and advection. And probably the biggest advantage is, one of the biggest advantages that we do the C14 analysis to make sure that we only account for all carbon when we quantify the rates. The disadvantage is that it takes about 4 weeks from the point we receive our traps until we do the reports. The gradient method, as I indicated, you have different samplers at different elevations in the ground, and you quantify gases of interest, typically CO2, methane, oxygen. You can quantify particular contaminants. When there's no reaction, the change in concentration with elevation is proportional to the flux, and the proportionality constant is the in-situ diffusion coefficient. However, the in-situ diffusion coefficient has a high uncertainty associated with it, because it not only depends on the type of soil, depends on the moisture, and also depends on the temperature. So it has to be measured at the same time that you measure the gas concentrations. It's a lot of work, it's labor intensive, and really the biggest limitation is that you need to address this in-situ diffusion coefficient. It assumes only diffusion as the transfer mechanism, which is probably a good thing at depth, but close to the surface you might have these changes in ambient pressure that create advective changes in concentration, and you need to account for that. So it has some limitations, but it does have its place. The advantage is that it's telling you at what depth things are happening, and you can apply it to other soil gas components. The dynamic flux chamber is similar to the traps in the sense that you put a receiver shallow pipe and then you put a closed chamber on top of it. The closed chamber is connected to gas meter, and you really track how fast the concentrations inside the chamber are changing to estimate the flux. The chambers are deployed for 5 minutes, approximately 5 to 7 minutes. So they are designed as a short-term measurement. However, these fluxes change quickly. This is data from, it's not from a contaminated site, but it's from a field. And what they did is they applied this method multiple times a day, about every half hour, and the fluxes change like that. So the soil, the gas really excels and inhales once a day based on ambient and temperature pressure cycles. So because of that, and also because it's really hard to do the C14 correction on this method, really this is, I consider this more of a screening tool. So this is a slide about the dynamics of soil respiration. This is a paper that is available on the internet, and this was co-authored by Arcadis and ExxonMobil. They went to a contaminated site. They put the dynamic closed chambers, an automated version that takes measurements every 30 minutes, and they did it for about 20 days. And this is what the time series looks like. And you see that you have these daily cycles. You also see that after rain, the fluxes are very low, sometimes even negative. And it's because if the pores get saturated with water, then really the gases have a hard time going across that boundary. They also applied our technique, and these are the numbers that they got from a location nearby to this one. And this shows that the total flux is in the range of what they measured, but it's variable because it wasn't the same location. But here, what is shown in red is the fraction that really came from all carbon based on the C14 analysis. And these numbers were highly repeatable. But this highlights that the signal is noisy, not only because of the time, but because the modern fraction of CO2 that is produced at each location depends on what is happening at that location. The limitation that I want to point out is that people typically don't deploy these traps, these chambers, measuring every 30 minutes. So they take something called a survey mode, a single chamber that you take to sites. So really, you have to characterize this time series based on a single number out of it, based on the time that you're spending at site. So, so that's a limitation, and really, the take home here is that you need to consider temporal flux changes based on diurnal cycles, or really temporal soil conditions based on precipitation when using soil respirometry to measure NSZD rates. So I'm going to shift gears here and give you some generic examples about how you can feed your conceptual site model from NSZD data. So the idea is, the generic idea is based on the triad approach. And the triad approach tells you that you should come up with a dynamic work plan, initially collect data that is perhaps of high uncertainty, but it's easy to get and relatively low cost, and you collect a lot of that, formulate your hypothesis, and then you can move up to the next tier with higher data quality, which typically means higher cost to confirm your hypothesis. And ultimately, you might want to rely on the best data to really kind of put a crown on this pyramid and build your conceptual model that side. As you go up in this pyramid, you have more quantitative methods. As you go down this pyramid, you have qualitative methods that are more line of evidence. So here's so really, you need to have a consistency between your monitoring goals and the monitoring plans, and you want to move in between both in a dynamic way. So a typical site, you want to build your multiple lines of evidence and ultimately do NSZD rate quantification. And the way you do that is with this logic here on the right. You want to know if NSZD is happening, do qualitative indicators coincide with source mapping, and then if that is the case, you want to see, is there vertical soil gas flow, because that's one of the assumptions of the mass and heat balance methods, and you want to identify locations for the quantification and ultimately do that if you get to the top of the pyramid with a C14 analysis. So here at the base of the pyramid, you would look at groundwater geochemistry. You can do gas headspace analysis from existing wells, and perhaps soil temperatures. And you, at this point in the middle of the pyramid, you might want to use the dynamic closed chambers. And if you really want to move forward and quantify, you might want to consider OS for that. That's kind of a typical progression that I see at sites. And ultimately quantify your natural source and depletion rates. So you might have a couple of questions here, which is why didn't you include the gradient method? Well, it's relatively labor intensive and expensive, but it has high uncertainty. So unless you really have the questions in advance that you want to answer with that particular method, you might not want to use it. And what about not using the temperatures for the thermal gradient? Well, I will go into detail about that in a couple of slides, but really it has to do with usability of the data and the uncertainty of the results. So here I am providing. So if you want to, why would you want to measure NSZD rates? Well, the point is that really the NSZD rates are comparable to active remedies. This is data that Tom Palaya published. It's on the internet, and he took a survey of 29 systems, and this is the range that he saw. These are box plots which have the 25, 50, and 75 percentiles, and he saw ranges of efficiency of these active remedies from a few hundred gallons per acre per year to a couple of thousand gallons per acre per year. And in a paper published in 2017, Sanjay Gar from Shell, they published this middle 50 percentile from the 25 to the 75 percentile. And the point of this slide is that NSZD can exceed active remedies. Of course, the range of active remedies is very large, and I want to elaborate a little bit on that. This is a typical generic performance curve for an active remedy. You have the annual performance. The first year, you get the highest performance, and that performance continues to decrease with time slightly. And But if you quantify the cumulative performance, it starts flattening it out at maybe 5, 10, 15 years and reaches this point that I call asymptotic performance, when it's flat. So initially, traditional remediation achieves high efficiency, but it becomes less efficiency. So how high can you get on that? Well, you might want to look at the literature, but at the Remedies side, they found that about 25 to 35% of the oil couldn't be retrieved. So all remedies typically can be below NSZDs, and perhaps if you have a remedy that was recently implemented, maybe that's still efficient and can achieve its goals. But after time, you might want to consider this concept that people are talking about, a remedy transition into something less intensive. So this is really a slide in which I'm really posing the same concept, but comparing the 100% of the original oil spill. And if you come and implement some remediation, you take credit for that. But really it's a very stationary mass balance. So you have here the maximum recovery of 25 to 35%, but if you take into account natural source and depletion kicks in every year, and every year sort of compounds after a number of years, and it can take you below the maximum recovery. And of course, you can quantify these NSZD rates in combination with whatever active remedies you might have implemented. But really, this is a different way of looking at the mass balance and taking credit for the losses to NSZD rates. So this is a different case study, a generic one, in which you might have a lot of data at your site, and you might know what is happening there, but there might be sensitive locations where it's hard to go in there. So you might want to use these surface NSZD measurements and use them as a screening tool to see if you have a high chance of having that location being impacted or not before you take additional samples or before you drill a monitoring well at that location. So in some cases, you might not be interested in quantifying NSZD rates. You might just want to show that it's happening, and you might not need to quantify those rates, or quantifying it might be really difficult because perhaps your site is covered with petroleum, so you collect the bottom of the pyramid, the middle, and really you leave that bottom of the pyramid pending until you figure out what is happening. But a lot of this information will build up into your conceptual site model. So I have some a detailed case study in which NSZD rate measurements were used with a remediation technique with Phytoremediation. And this is a case study. This was done by ITRC, a consulting company from California. And there's a webinar, a 1 hour webinar on our site published that you can check if you want to go into the details here. I'm only going to show about 4 or 5 slides about the high level rationale for this project. So they had a pump and treat system that had been operating for a number of years, but it was of questionable efficiency. So what they decided was look at phytoremediation. So phytoremediation is you plant trees, and the trees can have multiple effects on the hydrology and contaminant degradation rate. So the first one at the bottom is that the roots can take up water and depress the groundwater table and create a vertical flux of water similar to pumping. The second one is that the tree and the roots can take up some contaminant and immobilize it. The foliage can volatilize some components here as well. But really the big one here is the argument that the roots are providing a better environment for bacteria and improve the biodegradation rate. So what they did is they took NSZD NSZD rate measurements to prove if some of these were happening. Of course, they took groundwater levels, and it's a really interesting story. This is a map of the site. They started with a couple of plot areas that were tests, and they planted a bunch of trees. This is a grid of the tree plantation scheme. And what they did is they measured the CO2 fluxes at the surface, and they quantify the rate of production of CO2, but they also figure out how much of that really is from all carbon. So here they have an area that is a reference area, and it was also planted with trees, but here they have the largest number inside the contaminant source. And they did these measurements right around the plantation of the trees in 2017, and they came back twice per year and they measured the rates. So a year later, these are the rates as shown here. So wherever there's contaminant in trees, they saw a large increase in the total CO2 fluxes, but probably more important, they really were able to demonstrate that the all carbon fluxes had been increased. So the trees were increasing this biodegradation rate of the contaminant, and of course in 2019 the numbers were even bigger, and they had expanded the test to the entire site. So this is a plot that shows the reference areas that didn't have much contamination compared to the source. Here you see the seasonality of the measurement, but every year seems to be going up compared to the previous year. And probably more importantly, here, this is kind of the success story, is that this compares the NSZD rates that they measure after 2017 to the previous story of the pump and treat. So the pump and treat had maximized at about less than 1,000 gallons per year in 2015, and they started decreasing in efficiency, and now Phytoremediation is doing almost 2x and doing it in a more sustainable, lower carbon footprint manner, and also bringing considerable savings to this site. So I want to go into the last section of my presentation, talking about new developments. So this summarizes some of the new developments in the NSZD world. There's an ASTM working group that will have an ASTM guidance document in NSZD. We have started working on that and expect a final version in a few months. The second point here is that I've been talking about CO2 fluxes used for LNAPL degradation, but if you look at chlorinated solvents, the end products are ethene or ethane, and that's a 2 carbons chain without chlorine, that once there's oxygen at the surface, it degrades similarly to methane, so it produces a quantitative rate of CO2. So we started working with Dr. Tom Boyd, the PI for this ESTCP project at the U.S. Naval Research Lab. And we are looking at that. We have done multiple runs of samples at different sites, and we believe that these numbers are low, as you can expect, because the degradation of chlorinated solvents proceeds at a low rate. But at least in some cases, the numbers are measurable. So expect a report on this ESTCP project in the near future. So for the last three, I have a couple of slides, which is the thermal gradient method, the compositional change method, and some alternatives to measure NSZD rates at sites that are capped with concrete. So the thermal gradient method, you will see this in the ITRC guidance document. It's also included in the API document. And the basis is that when you have a reactive zone in the ground, it produces heat. So this shows that this reactive zone, with the heat being produced in red, but the heat needs to get out. And as the heat gets out, it produces this profile of temperatures with elevation. And you know, in the case of the methane degradation into CO2, that really is a highly exothermic reaction that happens over a very, very thin thickness. And the change in temperatures with respect to elevation out of that reactive zone can be used to determine the fluxes. And if you determine the total heat produced and divide it by the heat of the reaction, you can determine the rate of the reaction in a heat balance type of fashion, similarly to the mass balance of the CO2 methods. So this is a timeline of some of the things that have happened in that method. In 2014, Todd Ryrie and Bob Sweeney published this paper in 2014, and what they showed is that there's about a 2 degrees centigrade increase at locations that were impacted with respect to those that are not impacted. And CSU was already working on temperature things in the ground at that point, and they filed for a patent. And the patent from CSU includes background correction, meaning that difference of temperatures at an impacted and non-impacted location can be used to determine the heat rate of production. And shortly after, I started also working on doing some work on the thermal gradient, and I had filed for a patent in which I use temporal averaging over a long term to get rid of the interference from ambient temperature fluctuations. The CSU patent got approved in 2018 and mine in 2020. You will see this method well documented in basically naming guidance document. There's papers published mostly from the CSU method, which has been licensed to GSI Environmental. And GSI Environmental has an ESTCP project using this monitoring technique, and expect a report on 2022 about this method. However, the reference number 6 here is from last year, and what they did is they used 6 Australian LNAPL contaminated sites. They used multiple measurements at each site, and this was the conclusion. The conclusion was that the temperature gradient method was very difficult to reconcile with the rest. It had the biggest differences with respect to the other methods. So yes, there are sites where it works, but there are sites where it doesn't. So my recommendation is that if you measure temperatures at your site, that is useful information, but it's probably better suited as a line of evidence than to quantify. Perhaps the quantification will work, but you shouldn't bank on that in advance. You should look at the results before putting too much weight on that. So the compositional change method is, the basis is that some petroleum compounds have low solubility. They are very stable and show minimal biodegradation. These are called terpenes, and they are, chemically associated with rubber, really. And specifically C19 and C20, pristane and phytane, they are used as biomarkers. The idea is that they have low solubility, they don't biodegrade, so their mass in the source should remain constant. So at the Remedies site, which happened in 1979, the group from the USGS, led by Barbara Bekins, they took these samples, and this is a chromatogram from '83, which shows the composition. And here I'm highlighting these biomarkers, and they came back about 16 years later, and the biodegradable compounds have depleted, but these biomarkers are still there. So you can use that in a quantitative fashion to estimate the rate. Now, you need multiple samples with time. You need to be aware of where they collected. It's ideal if you can collect those from the soil rather than a well. And the biomarker selection is important. So the method provides relative degradation rate estimates for individual compounds. That is probably the biggest limitation, but also the biggest advantage. So these are some quotations from 2 papers, the one from Bekins in 2005, and recently last year there's a paper by the Shell group in groundwater monitoring and remediation, and this is what they said. That the first one is a warning from Barbara Bekins that the degradation mechanism changes the method. And the second one is that the emphasis that this is really a method that has a lot of leeway and is best used to estimate relative rates for constituent depletion. The last thing that I have here before I wrap up is that cap sites with concrete have been a challenge. All of the methods based on mass balances or heat balances rely on one-dimensional transports, and cap sites do not meet this condition. So one alternative was to open a large opening, probably as large as 6 by 6 feet, and the idea is that at the center of that opening, the wall effects from the presence of concrete have gone away. We have had a couple of sites at which that has been tried with good results. This one shown here is another novel solution in which you don't need to make a large hole in the ground. You make a little one and put a closed system with a solid well casing all the way into the water table, deep enough to plug it at the bottom with water. And now you have a one-dimensional system that you can monitor like a well-behaved system otherwise. And you keep the native formation inside the solid casing, so you keep the geochemistry, the soil microbes, the soil temperatures and variations, the lithology, the contaminant mass and distribution, and this is relatively simple. I call this an in-situ microcosm, and we have implemented at 2 sites with excellent results. Probably more importantly, because this is a closed system, the results are highly defensible. The limitation is that really this can only be applied to depths at which you can install direct push well casings. So I want to finish my presentation with really a wrap-up. I hope that I made the case that you can NSZD at your site for multiple things. You can delineate your LNAPL with non-intrusive methods. That provides guidance on where to locate monitoring wells and where to sample. The quantification of NSZD rates provides a reference mass loss rates to compare the performance of active remedies. This is a basis for a quantitative guide to remedy transition from remedy that is no longer effective to something more sustainable and in a data-driven framework. The NSZD is a remedy. It has been implemented at some sites, not for all sites, but it can be useful. It can be applicable to some sites. So really, that's all I have. That's my contact information. You can check our website for a lot of this information. You can contact me for a detailed list of some of the references that I mentioned in this presentation. And now I will pass this on back to Microbial Insights.
Julio, that was fantastic as always. I'm always very impressed by your presentation. And always been a fan of efflux. What a great technology. So before we move on to questions, which again, if you have any questions for Julio, please type that into the question panel for your GoToWebinar panel. And we'll get to those in just a second. But I wanted to follow up with this great presentation and webinar about some new news at Microbial Insights. So many of you are familiar with what Microbial Insights does and a lot of the tools that we offer. And I wanted to let you know that, again, relevant to what Julio is mentioning today, that our molecular biological tool family is growing. So specifically, we've been around for almost 3 decades, 29 years this year, coming very close to 30 years total. And within that time period, we have really kind of taken the torch and run with molecular biological technology. And some of the tools you're very familiar with include stable isotope probing, compound-specific isotope analysis, different passive sampling devices, including our own in-situ microcosm. I know Julio mentioned his in-situ microcosm, but of course we have our own advanced biotraps for that. But additionally, of course, kind of our flagship analyses are qPCR-based, our census, where you can select targets a la carte, or our quantarray analyses, which has an array of qPCR targets relevant to your site. So that being said, many of you are familiar with our quantarray chlor and our quantarray petro, but we have 2 new quantarray family members, including quantarray BGC for biogeochemical strategies. And then, again, relevant to today's talk, we have the quantarray NSZD, which is a selection of genetic targets relevant to natural source zone depletion. And so within that quant array, which is multiple gene targets selected specific for natural source zone depletion, we have targets relevant to methanogens, acetoclastic methanogens that can utilize acetate, which is very important for natural source zone depletion. We have things like iron reducers and biosurfactant producers, as well as slime formers. So lots of great new tools coming up for microbial insights, but specifically wanted to highlight our NSZD quant array, which I think will pair very well with some of these efflux analyses. And so if you have any questions about our quant array NSZD, I recommend that you reach out to us. You can email us at info@microbe.com, or you can go to our website at www.microbe.com and select our quant array NSZD. And there's a little handout in there that can highlight some of the targets that are on there as well. Again, our contact info at Microbial Insights is info@microbe.com. And as I pass on the presentation back to you, Julio, in case you need to share any slides, I'm going to look into some of these questions that we've been asked. We have a lot of attendees today, and thank you everyone who has attended today. We have some record numbers, and we have a lot of great questions. So first of all, I see that some people are interested in getting your presentation, and I know you shared your PDF with me previously. Is it okay if we send that out to folks that are asking for that, Julio?
Yes, you might want to wait until I send you the revised presentation because, consistent with my habits, I was doing some last-minute changes. So.
Of course, yeah, of course. That sounds great. No problem with that. Okay, great. Well, again, if you have any questions, please enter those into the questions section of your GoToWebinar software here on the side. And let's start with a couple of the first ones that we got. So someone had a question. They said that bioventing work has previously shown that CO2 is not the best way to quantify contaminant degradation rates because it is not conserved when it interacts with the soil. It can precipitate as carbonates. Do you have any thoughts on this and how that might affect some of the work that you're talking about?
Yes, good question, Sam. Thank you for that question. When the idea came out of quantifying the NSZD rates based on CO2 productions, there's a lot of work that was done by Uli Meyer. He did detailed chemical modeling on the surface. And he showed that really the precipitation of inorganic carbon in the soil column was minimal, would be only a couple of percentage points. We have had our traps used for this application, and we see a very high increase, a very high rate. So the rates at the surface are measurable, and for what we know, the accumulation within the soil is minimal. It's always a good idea to look into that either with some geochemical equilibrium modeling or perhaps taking some samples. But in our experience, these measurements of CO2 production are quantitative.
Great. That's great, Julio. Thank you. Karen asks, with groundwater at 300 feet below surface, will the use of efflux be effective since there may be a lot of dissipation of C14 CO2 that would not result in reliable rates?
Yeah, that's a great comment. Conceptually, the source is wherever the source is. If it's a small source, you can picture it as a point source. As the gases are moving up, they're moving in a kind of a cone pattern due to dispersion. And when you reach the ground, the one square meter at the source has been diluted into many at the surface. So the question here is not if the depth is very deep, but if the ratio of lateral extent of the contaminant versus depth. And we have had measurements at in some of the desert type of setups in California and Texas with very deep water tables, and we have made measurements at about, I believe, 150 feet or so. So I don't recall having done it at 300 feet, but I think that the question there is to look at the lateral extent. And at the edges of the source, you might see some of this dilution, but at the center, you might not.
Perfect. Great. Someone is asking specifically, have you come across the zero headspace sampling system Simul probe? And if so, would you say it was useful in doing the vertical gas profiling?
You know, I'm not familiar with that method. So really, I cannot comment on that. I think that there's many ways of sampling the vadose zone. One that I recommend is just to take a rough measurement on an existing well with a landfill gas meter and look at the relative compositions of CO2, methane, and oxygen. And an indication of methane there is useful. The zero headspace, I looked at it a while ago, but I don't have enough to look into that. But I would mention that you need to look at what are your screening intervals, and if this gets deployed into a wells, which I believe it is. But I think that any passive system that gives you more of an average than the instant, the well is a huge mixing cell, and I think that passive sampling there is probably the way to go.
Great. Julio, how frequently, this is kind of a broad question, but how frequently do you think an NSZD is occurring at LNAPL sites?
Yeah, that's most people, when you look for NSZD, most of the time you find it. It's very rare that you have an LNAPL contaminated site and you don't have NSZD. Petroleum is inherently biodegradable. For example, if you go to a forest and there has been a forest fire, and there's no petroleum there, but if you sample for PHA biodegraders, there are microbes that are degrading that partially charred wood. So microbes that degrade petroleum are conspicuous in the environment, and most sites that have petroleum contamination will show some signs of NSZD.
Great. In terms of the phytoremediation example that you provided, how do you isolate CO2 flux from the remediation versus from regular tree respiration?
That's a complicated question. A tree is heterogeneous, is very localized, and things are happening differently in the foliage than in the soil. And I am not an expert in this area. I don't think you can in an easy way. I think you can look at what is coming out of the soil, and if you want to look at what is happening in the tree, you might have to sample the tree itself or the respiration through the leaves. But this really is kind of going beyond my expertise. I would encourage you to look at the presentation that we have in our website. But I suspect that the answer to that question is not a simple one.
Got it. Okay. The next question is, how does background methane affect NSZD? That's an interesting question. I would say that background methane is typically, in my mind, is low. There can be some exceptions. If you have a swamp or so that is organic rich and close to the water table, you might see that. It's kind of rare. It could happen. I think that what I would be looking at is the C14 base, the radiocarbon base methods would help you with that, because even if there's background methane, when it burns into CO2, it will provide a monocarbon signature. We had a site in which we did measurements in soils that were organic rich, and we saw that there was a signature. But the carbon that is in the order of 10,000 years old or so should have stopped biodegrading a while ago. Now, if you have a swamp or so in which you have methane, natural methane,
you might have that situation. But again, you might want to look at the C14 methods to eliminate the interference of background organics.
Great answer. Now, you just mentioned how petroleum hydrocarbons are kind of readily biodegradable, but what about NSZD for things like DNAPL for heavier hydrocarbons?
Yes, we have had a few cases since the beginning. People were interested in DNAPL, and we have done measurements at DNAPL sites, creosote type of contaminants, and what we have found is that the rates are lower, but are there. And if you look at the geochemistry of the groundwater, you will see that DNAPL, even though it's supposed to be not very biodegradable, it will be degrading. You can use some of your qualitative tools or your other methods, and when you apply our method, we get rates that are probably a fifth of what you would see with fresh biodegradable petroleum, but the rates are measurable, and it might help you with your conceptual site model.
Fantastic. We have a question here. What was the model used to track soil gas analyses?
The model used for, I'm not sure I understand the question. I think it might be a reference to the gradient method, or do you know if that question is referred to the chromatograms that I showed?
I don't know. I would assume that it's also respective to the gradient method as well, which may be the answer. Yeah, go ahead.
I don't know. If you're referring to the gradient method, you can look at the paper from Paul Undergaard, or you can contact me for a detailed list of references that I used in this presentation. I'll be happy to provide that. I think it's really not that hard to, when you sample in the soil, you have to worry about two things. How you sample, and typically this is with multi-level samplers, which are little tubes that have a bit of a filter in the end. So you wouldn't sample from a well, you would sample from the formation. And then what kind of method you use to quantify those components, CO2, methane, or oxygen. And I suspect that there's some chromatography there, but I don't remember the details because I was from the gradient paper from Paul Johnson.
Great. So they can reach out and get that paper from you if they need to.
Yeah.
Here's one that I think we all resonate with. How do you respond to regulators that think that NSZD is not a remedial alternative and does not result in direct remediation of contamination at a site?
Yeah, that's a great question. The regulatory acceptance has been an issue since we started working on it, and I will say that we have converted some regulators, at least not all. But I would say that the discussion is really not about if NSZD should be of consideration, but it's, can we collect data and can we go where the data takes us? So, the science is there. There's multiple methods. There's lines of evidence. It is happening. The rates are well published, and if you really don't want to go there, it's probably because you have another reason that is really not based in data, and I think that's difficult. I see very strong differences between different locations, different states, Massachusetts, California, some other states. Internationally, we see this, where there's more of a collaboration and an agreement to use solid data. People can get to this agreement that NSZD actually makes sense, that it's not just snake oil.
Great. Yeah, absolutely. Here's kind of a twofold question from Brent. Can CO2 method be used to delineate the presence-absence of LNAPL migration to a site? And additionally, can it be linked to increases or decreases in LNAPL thickness over time?
Yes, for the first question, yes. We have multiple sites. People are using our measurements to at least get a screening measurement to whether or not there's contamination in the ground. at these suspect locations before they drill wells. The second one is really difficult. You know, the thickness of contamination, at least based on a well, is not always related to what is in the formation. You know, what is in a well depends on your saturations and how much of the soil is residual and the contaminant distribution. So if you have two sites with the same thickness, but it's all close together at one location, you know, these processes are surface area limited, and that surface is small, and you will get a small rate. If you have the same amount vertically, but it's distributed over a large smear zone, then more of the soil is participating in this process, and you might get a much larger rate. And this has been a difficulty from the beginning. We were trying to figure out, you know, are some contaminants producing higher rates than others? And the compositionally, we know that is true, but how do you measure that at sites? Because at sites, there's many other confounding variables, but one that is of particular interest is the distribution of the contaminant, and that is really difficult to figure out. So for the second question, I would say no, you need detailed information either from course or perhaps LIF, and really, in that case, you sort of need to go at the base of that pyramid and build it with the required information before saying, well, see, you know, we know there's a heavy thickness here and we're getting low numbers from the efflux numbers. Well, perhaps it's because it's all collapsed around the water table, or perhaps even submerged. So that's a difficult one.
Great. Yeah. Good answer. Good response. We have a question about the quantarray sampling, and we can, Microbial Insights can accept groundwater, soil, or biotrap samples. If you're unfamiliar with a biotrap, please visit our website or feel free to give me a call. And we'll do one or two more questions, Julio, and then for those of you who were unable to have your questions answered within our session time, feel free to email Julio at the email here shown on the screen. And then additionally, you're welcome to email us at info@microbe.com. Here's a question. How do the flux measurement devices differ from the older emission isolation flux chambers? And can you obtain emission rates per square foot to evaluate rates across the footprint?
Yes, the EPA had used chambers a while ago, and you know, so in some publication they refer to them as the EPA chambers. And what I understand is that it was the static chamber, meaning that it was just put on the ground and it was closed, and it really plugged the flow that you were trying to measure. So the dynamic chamber is different because it has a little hole on the top, and it allows for equilibration of the pressure inside the chamber with the outside. And also, this is deployed for a short time. So you know, there's a distinction there between the static chambers and the dynamic chambers. The dynamic chambers are more modern and is supposed to be a better number. Now, when they refer to emissions, you can use the chamber to estimate the emissions of contaminants. You know, emissions, I don't know if it's contaminants or CO2, but I'll touch into the contaminants. If you have the right sensor, or you take discrete samples inside the chamber for actual VOCs, you can estimate fluxes based on that. And there are some papers about that. I mean, in terms of CO2, really depends on the sensor you have. The most commonly one used is by a company called Lycor, and they use an infrared gas analyzer that is supposed to be a really good measurement. So I think that the question was it could be taken a couple of ways, and I hope I addressed both.
That's great. I think that's great. And if not, people can feel free to reach out to you. Yep. Last question. Your cover slide illustrates an important consideration for surface CO2 traps. In terms of macropores in the soil, do they bias the results since CO2 will move up through those avenues preferentially?
Yes, you have to be careful about preferential flows in the ground. So the installation of the receiver, we recommend that you direct push it and create a minimum disturbance in the ground. and leave the inside of the soil as undisturbed as possible. So you can have a little disturbance around the seal of the receiver pipe. If that is a concern, you can go to a higher capture area. We have 8-inch receivers, and then you'll be not only averaging over a larger area, but the ratio of your perimeter to the area becomes smaller. And it is thought that as long as you have a good seal on the outside, there's a lot of work based on done on that, a lot of that done in chambers, but developing these protocols for installing your connection with the soil is very important. And you know, something else that happens that you might want to be aware of is when you have like fractured rock and it's very shallow, you have a shallow overburden, your gases might not have enough space to redistribute themselves and leave the ground uniformly. So again, I think this might be a situation in which the chamber might be a good screening instrument to just understand what is the scale at which the variabilities are happening if you have these cracks in the surface where most of the flow is leaving.
Perfect. Great. Well, with that, Julio, thank you so much for your insight, your knowledge, and experience that you shared in the presentation today. And thank you, everyone, for the thoughtful questions. If we didn't get to your question, again, feel free to email Julio, email us at info@microbe.com. If you have questions about the quaternary NSZD, feel free to check out the website, or again, email us about your site and whether you think it would be a good match for your site. Thank you, everyone, for taking the time today. Again, this is a recorded webinar, so you should see it within our webinar tab on our website at microbe.com within the next week, and keep an eye out for your email for a link to that webinar recording directly. And again, Julio, thank you so much for your time. I'm Sam Rosalina, Director of Research and Development here at microbe.com, Microbial Insights, and thank you all again for attending this great webinar.
Sam, thank you very much for hosting, and thank you, Microbial Insights. It has been a pleasure.
Absolutely. Thanks.